Sir, good morning, sir.
Yes, good morning. Tell me.
Actually, yesterday's class PDF ninth problem was missing, sir.
Yesterday's class PDF,
Ninth problem was missing, sir.
ninth problem was missing. Okay,
Yes,
I
sir.
will update.
Okay, sir.
I'll update. So, probability lecture number 5. Welcome to all unmatchable people in this unmatchable session on unmatchable platform. So, as promised yesterday, that now we are going to start understanding compound random experiments. Now we are going to start understanding compound random experiments. And that's going to be the next phase of probability, let's say probability 2.0. So in the very first chapter, we are done with probability 1.0. Probability 1.0 and probability 1.0, we dealt with number 1, 3 axioms of probability. Number 1, 3 axioms of probability. Number 2, number 1, 3 axioms of probability. And then number 2 is what? Number 2 is finite single sample space. Finite single sample space, and you can define multiple events in that sample space. There was one more condition here: finite single sample space with equally likely outcomes. I say it again, that no resource actually covers probability in such a defined and such a systematic way. No matter which book, which video, which lectures somebody is going to refer, it's not about bragging. It's about my own struggle. When at the time of my thesis, I was trying to learn probability, I struggled a lot because there was not even a single resource where a very systematic address was done to the subject. First of all, the very big thing in which I struggled was this, that I found this formula not applicable in so many instances. And yet I found most of the books starting with this definition of probability. And I was like, this can't be the beginning of the whole subject. Luckily, there are resources which enlightened. The beginning of the subject is actually these axioms. And then we covered addition law of probability. The third thing that we touched was addition law of probability. Addition law of probability. So let's quickly, very quickly, recapitulate these three things before we move into the next big thing. And the next big thing is to consider multiple sample spaces together. So, as far as three axioms are concerned, for one last time, I want to say axioms are like some belief, axioms are like some core truth, axioms are like some common belief. For example, for example, example, this is worth 100 rupees. What is the proof? Can somebody prove that this is worth 100 rupees? Huh? That this can buy 2 kilograms of wheat flour? This is just a common belief. This is just an axiom that let's make something and let's believe that it represents 100 points. Other than that, there is nothing. This is just a common belief. That's it. That there is something existing which represents 100 points. So just like that, axioms are, now this is of course a virtual thing. Probability is not a virtual thing. Probability actually is there. Randomness is actually there. So it's our belief about probability and it has never been proved wrong. So what is the first belief? First belief is that probability of any event is never going to become negative because worst case, that event will not happen. It will have zero chance. Least it can have zero chance. Second axiom of probability is that probability of whole sample space will always be 1. Why? Because something will happen. Sample space covers every possibility. So one or second thing or third thing or fourth thing, something will happen. And then there is a third axiom. And third axiom is that probability of A union B will be equal to probability of A plus probability of B. Probability of A union B will be equal to probability of A plus probability of B, given that A and B are mutually exclusive. Given that A and B are mutually exclusive. So we have the first axiom, we have the second axiom, and we have the third axiom. Then we entered into the finite sample space, finite and single sample space with equally likely outcomes. Using axiom number 2, we can write, if we use axiom number 2, we can write the probability of total sample space as 1, probability of total sample space as 1, and then total sample space is nothing but union of all elements of that sample space. Let's say that sample space has capital N number of elements. So just total sample space is simply the union of all elements belonging to that sample space is equal to 1, which I can write probability of E1 separate. Now I'm using axiom number. Now I'm using axiom number 3. So probability of E1 separate, probability of E2 separate, and so on and so forth. Probability of En separate. Probability of En separate. Now, probability of E1 can be, because all of them are equally likely. So I get small p plus small p plus small p, and I get this capital N number of times. I get this capital N number of times. So I get p multiplied by capital N is equal to 1. I get the probability of each outcome 1 upon capital N. Now suppose an event is defined on the same sample space. No, this was not an event. This was not an event. This was not an event. This was what? This was probability of each outcome. That's why we are representing a small p. That's why we are representing a small p. Now we move on to capital P. Capital P of any event that contains n number of outcomes. So naturally, it can be written as E1 union E5. I mean, let's say I want only E1 and E5. I don't want E2, E3, E4. And then let's say next I want E8. And then next, let's say I want E11. So like that, there are n number of outcomes that make up my event. There are capital N number of outcomes that make up whole sample space. And there are small n number of outcomes that make up my event. The event is you remember? The event is a part of the sample space in which we are interested. Event is a part of the sample space in which we are interested. So even, so like this, I have small n favorable outcomes. Small n favorable outcomes. Favorable outcomes means the outcomes that satisfy my event. Those outcomes which satisfy my event. So I'm going to get probability of E1 and union means what? Union means plus, and probability of E5 and probability of E5 and probability of E8 and probability of E small n. Now we are adding 1 upon n, 1 upon n, 1 upon n, 1 upon n, small n number of times. By the way, make sure that you are, before solving DPPs, you complete class problems once by yourself without looking at solutions. Because every class problem that we have done will make you very strong. So probability of such an event is going to become what? You're adding 1 upon capital N, 1 upon capital N, 1 upon capital N, 1 upon capital N, small n number of times. So it will become a small n upon capital N, which we call favorable number of favorable outcomes divided by total outcomes. Then we entered into the third thing, addition law of probability. Addition law of probability is based on inclusion-exclusion principle that we, in set theory, we have studied. Recall, in set theory, we have studied. Recall that in set theory, we have studied inclusion-exclusion principle. Isn't it? Just a moment. So recall that in set theory, we have done this. A union B is number of elements in A plus number of elements in B minus number of elements in A intersection B. Now, if I divide by capital N, divide by capital N, divide by capital N, divide by capital N, then this will become probability of A union B. This will become probability of A this will become probability of B, and this will become probability of A intersection B. Okay. Now, A intersection B. Now, same thing can be done for three number of sets, that A union B union C, A union B union C, and I have number of elements present in A plus number of elements present in B plus number of elements present in C minus number of elements present in A intersection B minus number of elements present in B intersection C minus number of elements present in C intersection A, and plus number of elements present in A intersection B intersection C. A intersection B intersection C. Now, once again, we divide by n, divide by n, divide by n, divide by capital 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 N. And all these values become probability values. So we get probability of A union B union C. Solve yesterday's DPP. You will get some really good problems based on addition law of probability. Solve yesterday's DPP. You'll get some really good problems based on addition law of probability. Kal ka DPP solve karo. And this becomes probability of A plus probability of B plus probability of C minus probability of A intersection B minus probability of B intersection C minus probability of C intersection A, C intersection A plus probability of A intersection B intersection C. ध्यान से समझियो, everything that we have done in probability presented to you in 10-15 minutes again. Everything that we have done in probability so far presented to you in 10-15 minutes once again. Now we move on to something really interesting, important, and the next phase of probability, that is probability 2.0. So let us go ahead to understand the probability 2.0. Probability 2.0 is what? I told you yesterday that now we are going to perform two random experiments simultaneously. Now we are going to perform two random experiments simultaneously, okay? And that's called a compound random experiment. So in probability 2.0, we start with compound random experiments. Now, before I tell you something, it's better to take some examples of compound random experiments. Let's take example number 1. Let's take the very first example of tossing a coin and rolling a die. Tossing a coin and rolling a die. Now, tossing a coin is one random experiment. Okay. And rolling a die is another random experiment. Do they have similar sample spaces? No. Even if they had similar sample spaces, even then, they are two different random experiments. They are not just one thing. Tossing a coin and rolling a die, they are just two different random experiments. One random experiment we are going to denote as E1. Another random experiment we are going to denote as E2. Now, tossing a coin has its own sample space where we are going to list two possibilities, head and tail. And rolling a die has its own sample space where we are going to list all its six possibilities, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So we have this tossing a coin existing and it has its own sample space. Tossing a coin is one random experiment having its own sample space. Rolling a die is another random experiment having its own sample space, where the total number of elements present in the random experiment, tossing a coin is 2, and the total number of outcomes, total number of possible outcomes Total number of possible outcomes in our second random experiment is 6. So let's try understanding that there is one random experiment E1 having sample space head comma tail, which is total 2 outcomes. There is another random experiment rolling a die E2 that has sample space 1, 2, 3, 4, 5, 6 having total 6 outcomes. There is one random experiment E1 having sample space head comma tail having total 2 outcomes. There is another random experiment rolling a die E2 that has sample space 1, 2, 3, 4, 5, 6 having total 6 outcomes. Now, treating whole thing as one random experiment, can you tell me what's going to be the sample space? Treating whole thing as one resultant combined random experiment. Treating the whole thing as one resultant combined random experiment. Combined random experiment, the resultant random experiment, the overall random experiment. The overall thing is obviously a random experiment, and I'm going to define a resultant random experiment E. A resultant random experiment E, what will be the sample space of that resultant experiment? That resultant experiment can give you head and 1, can give you head and 2, can give you head and 3, can give you head and 1, can give you head and 2, can give you head and 3, can give you head and 4, can give you head and 5. It can turn head and 6, and then tail and 1, tail and 2, tail and 3, tail and 4, tail and 5, and tail and 6. I realize that the resultant random experiment has total 12 outcomes. The resultant random experiment has total 12 outcomes. Resultant random experiment E, that's performed by simultaneously performing random experiments E1 and E2 has a sample space S
Sir,
having
your voice is
wait wait
getting
wait
breaking, sir.
Acha, voice is getting
Voice, sir,
broken.
voice.
Okay, all others,
No,
all other
sir.
people.
No, sir.
No,
No,
sir.
sir. Fine, sir.
Acha. So it's your internet problem in that case because all others are not facing.
Okay, sir.
Hmm. So, tossing a coin is one random experiment, and rolling a die is another random experiment. And we perform a random experiment by performing these two random experiments simultaneously. There is one random experiment being performed here by performing these two separate random experiments simultaneously. We perform tossing a coin also, we perform rolling a die also. Okay. And by performing these two random experiments, we perform this resultant random experiment. My dear friends, this resultant random experiment E has a sample space of 12 equally likely outcomes. Of 12 equally likely outcomes. And it's anybody's guess that it's 2 multiplied by 6 only. It's anybody's guess that it's 2 multiplied by 6 only. So what is the number of equally likely outcomes that resultant random experiment is having? The resultant random experiment is having the total number of equally likely outcomes, which is 12, which is actually 2 multiplied by 6, which is actually n1 multiplied by n1 multiplied by n2, which is actually n1 multiplied by n2. We will take just one more example to make sure that we understand this whole thing. We'll take just one more example. Example number 2. As an example number 2, let's say let's say we are having tossing a coin and drawing a card. Tossing a coin. We are tossing a coin and then we are drawing a card from the pack of 52 cards. Drawing a card from the pack of 52 cards. So now we have defined one random experiment E1 and we have defined another random experiment E2. This random experiment E1 has its own sample space, head and tail, which is total number of 2 equally likely outcomes. And this random experiment E2 has its own sample space, total 52, from the ace of spade and a king of spade to second card of space. And then, so this second random experiment has its own sample space in which we have 13 cards belonging to spade and then 13 cards also belonging to club, ace of club, king of club, up to the two of club, and then ace of diamond and king of diamond, and up to the two of diamond and ace of heart and king of heart, up to two of heart. So this second random experiment has its own sample space of 52 equally likely outcomes. There are 52 equally likely outcomes. But now I'm defining a random experiment of doing both these things simultaneously, doing both these things together, tossing a coin and also drawing a card. Tossing a coin and also drawing a card. So now if we are performing these two random experiments simultaneously, we call that combined thing as compound random experiment. The combined thing is called as compound random experiment. So the resultant random experiment or compound random experiment, the resultant random experiment or compound random experiment, we got to have resultant random experiment or compound random experiment that will have the sample space capital S, which is made up of 2 into 52 possibilities. How? Because I can combine all these possibilities with H, head coming with this, head coming with this, head coming with this, head coming with this, head coming with this. And then I can combine all these possibilities with tail also. Tail coming with this, tail coming with this, tail coming with this, tail coming with this. So head is coming and ace of spade is coming, and then head appears and king of uh, spade appears, and then similarly head appears and two of spade appears, and so on and so forth. Same thing we repeat with head, and same thing we repeat with tail, same thing we repeat with tail. So resultant random experiment has 2 multiplied by 52, that is 104 number of 104 number of equally likely outcomes. Once again, people, we have random experiment E1 having its own sample space S1 of n1 number of equally likely outcomes. We have random experiment E2 having its own sample space S2 of n2 number of equally likely outcomes. Then the compound random experiment E that's get performed by performing E1 and E2 both will have a sample space of capital N number of equally likely outcomes, where capital N is simply the product of N1 and N2. Let's write this rule. Let's write this rule. If random experiment, if random experiment E gets performed by performing random experiments E1 and E2 having sample spaces S1 of N1 equally likely outcomes and sample spaces S2 of N2 equally likely outcomes, then the compound random experiment E will have sample space S of capital N number of equally likely outcomes, where capital N is simply the product of N1, N2, N3, N4, N5. Let's write this. Regarding compound random experiments, let's write this. Okay, let's go ahead and write this. Now we are going to write this whole statement. If you want, I'll let one example written here so that you can correlate. Okay, so one example is still written so that because it's going to be a big statement that we are going to write now. If or let random experiment E gets performed by performing random experiments E1, E2 by performing random experiments E1, E2, E3 up to EK having sample spaces S1, S2, S1, S2, S3, and SK of N1, N2, N3, and Nk number of equally likely outcomes, number of equally likely outcomes, then the compound random experiment E then the compound random experiment E then the compound random experiment E will have sample space S will have sample space S of capital N number of equally likely outcomes capital N number of equally likely outcomes where capital N is N1 multiplied by N2 multiplied by N3 multiplied by Nk. I hope you understand. Now, when you read this, you get a clear feeling because we have already understood. We have already understood through two examples. But we are not only interested in the total number of outcomes, we are actually interested in now an event defined such that it gets satisfied by some sub-event on S1 and some another sub-event on S2. This was only finding out the total number of possible outcomes in such a compound random experiment. So now we know in such a compound random experiment, how many total outcomes will be there. For example, if I roll 3 dice, what will be the total number of outcomes? If I roll 3 dice, what will be the total number of outcomes? I'm asking this to you guys. For example, now I say
Sir,
216.
216, sir.
3 dice are rolled. Then if 3 dice are rolled, what will be the total number of outcomes? 6 into 6 into 6, that becomes 216. And if a die is rolled and a card is drawn, what will be the total number of outcomes? If a die is rolled and simultaneously a card is drawn from a pack of 52 cards.
312, sir.
312. If a die is rolled, and a card is drawn, then die rolled 6 possibilities, card drawn 52 possibilities. Total number of outcomes will become 52 into 6. That is 312 number of outcomes. That is 312 number of outcomes. Cool. If a student is selected from class 10, having total 50 students, and another student is selected from class 11, having total 40 students, then how many total outcomes are possible?
2000, sir.
Exactly, 50 multiplied by 40, that is 2000 total possible outcomes. If a student is selected for some sport event or for some representation of the class as a CR, as a monitor from class 10, having total 50 students, and one student is selected from class 11 also, having total 40 students, then total number of possibilities of monitors will be how many? 2000 possibilities will be there of having monitors, having representatives of the class. Cool. Such a big outcome, no? There will be 2000 possibilities of having representatives from both the classes. All right. Now we understand compound random experiment, but we are not only interested in total number of outcomes. We are actually interested in defining some event on. We are actually interested in defining some event on the resultant sample space that gets satisfied by defining its child events, children events on sample spaces S1 and S2. For example, let's try understanding for one last time before we move on. Tossing a coin is one random experiment, E1, having its own sample space, head, comma, tail, having two equally likely outcomes. Rolling a die, that is another random experiment, E2, having its own sample space, 1, 2, 3, 4, 5, 6, total 6 number of equally likely outcomes. But now I define a random experiment by co-performing both these random experiments, that I will toss a coin also and I will roll a die also. I will toss a coin also and I will roll a die also. Okay, I'll toss a coin and I'll roll a die. And that's how we define resultant random experiment. That's how we define resultant random experiment E. And that resultant random experiment will have 2 multiplied by 6, total 12 number of equally likely outcomes. That's why I have written here, if a random experiment E gets performed by performing random experiments E1 and E2 and E3 and EK, having sample spaces S1 and S2 and S3 and SK, and these sample spaces have N1, N2, N3, and K number of equally likely outcomes, then the compound random experiment that gets performed by performing all these random experiments simultaneously will have sample space S of capital N number of equally likely outcomes, where capital N is simply the product of N1, N2, N3, N4, N5, N6, N8, N9, N10, N11. Now is the time to define an event on resultant random experiment. Let's define an event on resultant random experiment or resultant sample space. Define an event on resultant sample space. Let A be an event. Let A be an event on resultant sample space capital S that gets satisfied by simultaneous occurrence of event A1 defined on S1 and event A2 defined on S2. Let us define an event A on sample space capital S that occurs by simultaneous occurrence of an event A1 defined on sample space S1 and an event A2 defined on sample space S2. An event A1 defined on sample space S1 and an event A2 defined on sample space S2. Then how we calculate the probability of this event A defined on sample space S. Again, let's try to do it through some example. Let's try to do it through example, and then we will be able to conclude something. So let's take an example. Let's define an event on sample space capital S that getting a head and a number, getting a head and a number greater than 4, getting a head and a number greater than 4. ध्यान से समझियो. So now getting a head and a number greater than 4. Total number of outcomes are how many? Total number of outcomes are 12. How many are favorable? How many are favorable? Favorable are head and 5 and head and 6. Getting head and a number greater than 4. So you can get number greater than 4 only in two possible ways, that is 5 and 6. What will be the probability of such an event? The probability of such an event is going to become 2 divided by 12. The probability of such an event is going to become 2 divided by 12. I can always write 2 as 1 multiplied by 2, and I can always write 12 as 2 multiplied by 6. And I notice I have 1 upon 2 separate, and I notice I have 2 upon 6 separate. Now you realize that 1 upon 2 is actually the probability of getting a head with on random experiment E1 without even bothering about that you are rolling a die simultaneously, without even bothering about that you are also rolling a die simultaneously. You don't bother about it. If you just think about getting a head here, you'll get probability 1 by 2 and 2 by 6. Notice that is representing getting a number greater than 4 in rolling a die. In rolling a die. My dear friends, I get probability of resultant event defined on resultant sample space capital S as the product of its children events A1 as the multiplication of its children events A1 and its children events A1 and A2 defined on the children sample spaces S1 and S2. Whatever you see in front of your eyes is called as multiplication law of probabilities for independent sample spaces. Of course, tossing a coin and rolling a die doesn't affect each other. Tossing a coin and rolling a die doesn't affect each other. Let's take one more example before we conclude the final statement. Let's take one more example. If you want avoid mugging up, if you want avoid scratching your head in probability questions, then make sure that you understand very attentively. Otherwise, people will not be able to figure out that, sir, when should I use addition law of probability and when should I use multiplication law of probability? I don't understand ever. Multiplication law of probability is strictly for multiple sample spaces, but these sample spaces are independent of each other. The outcomes of a die are never going to bother the outcomes of tossing a coin, and outcomes of tossing a coin are never going to bother the outcomes of rolling a die. Outcomes of rolling a die are totally unbothered, independent from outcomes of tossing a coin. So they are independent of each other. Let's take one more example. So we are on probability 2.0, and we have already concluded that if a random experiment E gets performed by performing experiments E1, E2, EK, having sample spaces. So when set theory and basic terms were going on, you thought that probability is such a basic thing, no? And now when these theorems are being written, मैथ्स की प्रैक्टिस के लिए ग्रेवाल ठीक है, बिल्कुल ठीक है, बढ़िया बुक है ग्रेवाल. Covers pretty much good amount of possibilities. But XC के लिए थोड़ा केयरफुल. अगर XC के लिए करते हो तो थोड़ा केयरफुल. Be a little careful. So having sample spaces S1, S2, having sample spaces S1, S2, SK containing N1, N2, NK number of equally likely outcomes, then experiment E, then experiment E will have sample space S containing capital N number of equally likely outcomes, where capital N is what? Capital N is simply N1 multiplied by N2 multiplied by N3 multiplied by Nk. This is something we understood through multiple examples, and now we have written it also twice. This whole rule is something that we understand. So let's take another example. let's say we roll 2 dice. We roll 2 dice, or you can rather write it roll 1 die and roll 1 more die, roll another die or second die, roll 1 die and roll the second die, and ask a person if he, she is a doctor, engineer, CA, or lawyer. Roll 1 die and roll a second die and ask the person at the same time that whether that person is a doctor or that person is engineer or that person is CA or that person is a lawyer or that person is a lawyer or that person is none of these. And let's say there is equally likely possibility of a person being either a doctor or an engineer or a CA or a lawyer or none of the above. Let's assume. That's an assumption, of course. Now, if you are performing this whole thing as one setup, then you have rolling 1 die defined as one random experiment, having 1, 2, 3, 4, 5, 6, total 6 number of equally likely outcomes. And rolling the second die is another random experiment. Having its own sample space 1, 2, 3, 4, 5, 6.
Sir. Some noise is coming, sir.
Some noise is coming?
Yes, sir.
Somebody has not muted actually.
Pawan Kalyan.
Yes, Pawan Kalyan. No, Pawan Kalyan is a big celebrity, no, so I can't say anything to him. So roll a die and then roll a die again and ask the person if that person is a doctor or that person is an engineer or that person is a CA or that person is a lawyer or that person is none of the above. And let's assume that a person becoming doctor or engineer or CA or lawyer or none of the above, let's say all of them are equally likely. Though it's not really the case. In India, a person being engineer is much more probable, no? Than any other profession. So random experiment E1 has sample space 1, 2, 3, 4, 5, 6, having total 6 number of equally likely outcomes. Random experiment E2 again has total 6 number of equally likely outcomes. And random experiment E3 asking a person what profession he has, that is third random experiment, and that random experiment has 1, 2, 3, 4, 5. 5 possibilities. He might answer doctor, he might answer engineer, he might answer CA, he might answer lawyer, he might answer none of the above. So there are total 5 number of outcomes. So if I see whole thing as one random experiment, combined setup, the compound experiment, then that compound experiment has how many? That compound experiment has how many total possible outcomes? If I see the whole thing as compound random experiment, resulting random experiment, combined random experiment, if I see the whole thing as resultant random experiment, my dear friends, its sample space is going to be sample space is going to have too many elements. We can't even list all of them. So you get one, and you get the response as doctor. You get one, and you get the response as engineer. You get one, and you get the response as CA. You get one, and you get the response as lawyer. You get one, and you get the response as none of the above. Then 1 and 2 and response as doctor, then 1 and 2 and response as engineer, then 1 and 2 and response as CA, 1 and 2 and response lawyer, 1 and 2 and the response as none of the above, 1 and 3 and doctor. Now listen, in the first random experiment we are still dealing with the only first outcome, 1 and 3 and doctor, and then 1 and 3 and engineer, and 1 and 3 and CA, and 1 and 3 and lawyer, and 1 and 3 and none of the above. So like this, if you keep listing, you will have, believe me, my dear friends, total number of 6 multiplied by 5 equally likely outcomes. Total number of 6 multiplied by 5. Total number of equally likely outcomes. So how many total number of equally likely outcomes are there? Total number of equally likely outcomes are 36 into 5, which
180,
is
sir.
180, exactly. Total number of equally likely outcomes, I have 180. Now suppose I define an event. Of getting a number less than 3 and either an engineer or a lawyer. Now suppose I define an event, a combined event, a resultant event of getting a number less than 3, Wait a moment,
Sir,
I'm coming back.
Hello.
Now suppose we define an event, a simple event of getting a number less than 3 on each of the dice and getting a response of being lawyer. That's it. Let's keep it simple. Let's keep it super simple. Getting a number less than 3 on each of the dice and getting lawyer as the response. My dear friends, getting a number less than 3. Now you try finding out how many are favorable to your event you just defined. So what is the event that we are defining? Event that we are defining is what? Event that we are defining is getting a number less than 3, getting less than 3 and getting less than 3 and getting less than 3 and getting the response as lawyer. This is the event we are defining. How many total favorable outcomes are there? Try counting. Don't try to making any rule. Don't try to make any algorithm here. Just try to do simple counting. That how many out of these 180 total possibilities, how many favor you? So I'm getting a number less than 3 on each of the dice and getting lawyer, one favorable event. Getting a number less than 3 on each of the dice and getting a lawyer is second favorable event. This is the second favorable outcome. And then we are going to have, let's try to list more favorable outcomes. First of all, avoid making any rule, avoid making any law, avoid making any law, any rule. No, nothing, no, please. Just do the simple counting on resultant sample space. You have, forget and pretend that there is no E1, there is no E2, there is no E3, there is no S1, there is no S2, there is no S3, there is no N1, there is no N2, there is no N3. There is only one experiment having 180 total outcomes. Pretend for a moment for me that there is no rolling a die separate, there is no rolling second die separate, and there is no asking a person separate. Pretend that it's just one thing you are doing. And if it's just one thing you are doing, it has 180 possibilities. Out of 180 possibilities, I have this favorable outcome. I have this favorable outcome. Let's try to list all favorable outcomes. So I have some more favorable outcomes, getting greater than 3, getting greater than 3, and getting lawyer as the response. Sorry, getting less than 3, and getting lawyer as the response. So I 1L, 12L, and then there is one more possibility, and that possibility is 21L. Isn't it? That possibility is 21L. And there is one more possibility, 22L. There is one more possibility, 21L, and there is one more possibility, 22L. Now, I have 4 favorable outcomes, isn't it? 11L, 12L, 21L, and 22L. Other than these 4, there is no other possibility. So what's going to be the final answer of this question, that getting less than 3, getting less than 3, and getting lawyer? How many total favorable things are there? 4. How many total favorable things are there? 4. And how many total outcomes are there? Total outcomes. I just need to make this whole thing little smaller. Otherwise, I will not be able to conclude on the same page. Chalega, no problem. So this whole thing I'm getting as 4 divided by 180. Now, 4 divided by 180, 4 can be broken into 2 into 2 into 1, and 4 can be broken into 2 into 2 into 1, and 180 can be broken into 6 into 6 into 5. My dear friends, 2 divided by 6 and 2 divided by 6 and 1 divided by 5, believe me, are the probabilities of getting less than 3 on sample space S1 and getting less than 3 on sample space S2 and getting 2019 के सितंबर में आपकी स्लाइड्स इतनी ऑर्गेनाइज्ड नहीं होती थी, बट अब बहुत ऑर्गेनाइज्ड होती हैं। शर्मा जी, तब मैंने ऑनलाइन वर्ल्ड में पदार्पण ही तो किया था। इसी को तो कहते हैं persistence, इसी को तो कहते हैं repetitions, कि आप किसी चीज पे लगे रहो लगे रहो लगे रहो तो परफेक्शन अचीव होता ही होता है. There is no other. If somebody keeps pursuing a dream, keeps pursuing a passion, perfection eventually comes. Problem is that many people, when they don't see the results yet, they don't get convinced. Hanji, so I realize that 2 upon 6 is simply the probability of getting a number less than 2, getting a number less than 3 in rolling one die. 2 divided by 6 is again simply the probability of getting a number less than 2 on rolling second die, and 1 upon 5 is simply the probability of getting lawyer as the response when you ask the profession of a person and he has 5 choices given, and let's say all 5 choices are equally likely. Let's say all 5 choices are having equal chances. This is wonderful. Why? Because if we had to count these many possibilities again and again and again and again and again, it would have been a nightmare. If we have to count these many possibilities again and again and again and again and again, and listing all the possibilities of a compound random experiment, it would become a nightmare. My dear friends, multiplication law of probability is a lifesaver. 2 divided by 6 is simply the probability of event A1 that was defined on first sample space. 2 divided by 6 is again the probability of simply the event A2 that would have been defined independently on the sample space S2. 1 divided by 5 is simply the probability of 1 divided by 5 is simply the probability of event A3, which is defined as the event of being a lawyer independently on third sample space. Independently on third sample space. Let's now write the statement of multiplication law of probabilities. Let's now write the statement of multiplication law of probabilities. We are defining an event A, a parent event A, that gets satisfied by performing child events A1 on sample space S1, A2 on sample space S2, and A3 on sample space S3. Then probability of this parent event A, probability of this parent event A occurring on the sample space, S of compound random experiment E will be equal to simply the product of probabilities of its child events A1, A2, and A3. As I said again, it will be simply the product of probabilities of its child events A1, A2, and A3. Let's write the statement of multiplication law of probabilities. Hmm. Here is the law. Here is the law. Let us now write the law, the multiplication law. If event capital A defined on sample space capital S of experiment E of experiment E occurs by co-occurrence of if event A defined on sample space S of experiment E. In fact, you can delete this much because you know capital S belongs to E. If event A defined on sample space S occurs by co-occurrence of occurs by co-occurrence of children events A1, A2, A3, AK defined on sample spaces S1, S2, SK. So event A occurs by simultaneous occurrence of many children events A1, A2, AK. And these children events have been defined. A1 has been defined on S1, A2 has been defined on S2, AK has been defined on SK. Okay? If event A defined on sample space S occurs by co-occurrence of children events A1, A2, A3, A4, AK defined on sample spaces S1, S2, S3, S4, SK, then probability of this event A will simply be equal to probability of product of probabilities of children events A1, children event A2, children event A3, and children event AK, and children event AK. Okay, this is called multiplication law of probabilities. This we call as multiplication law of probabilities. Saying it once again, event A is defined on sample space S, resulting event A defined on overall sample space S, having events A1, A2, and AK, defined on sample spaces S1, S2, and SK. Then please do remember multiplication law of probabilities. Multiplication law of probabilities can also be abused sometimes. I mean, you end up using multiplication law where multiplication law can't be used. There will be instances where you end up using multiplication law when it can't actually be used. I have seen people using addition law of probability when it can't be used, and also multiplication law of probability when it can't be used. There is a forever confusion. Adi anadikal se chala raha confusion in people's minds, that when multiplication law of probability should be used and when addition law of probability should be used. Addition law of probability can be used. Addition law of probability can be used when you are writing something on a single sample space. Multiplication law of probability can be used when a single sample space can be broken into children's sample spaces. A single sample space can be broken into children sample spaces. Then you can use multiplication law of probabilities. But we are going to have number of problems based on combined application of these two laws. Addition law of probability and multiplication law of probability. And we will now do such problems. We will now do such problems. Let's go ahead and try doing such problems. Dhyan se samajhiyo. Let me just write this before saving the slide, that this was the first thing that we did here, and the heading is, earlier I wrote compound experiment, but the real discussion finally is multiplication law of probabilities. Multiplication law of probabilities. Okay. So let's try solving some problems. You tell me, what's the score? Tell me what's the score?
11, sir.
11. Okay. So as an 11th problem, let's say we have, as an 11th problem, and by the way, we are going to solve these problems by having these problems we are going to solve by problems that we are going to solve now. They are actually the problems based on, let's solve one or two problems simply, one or two problems based on simply multiplication law. For example, suppose 3 dice are rolled. 3 dice are rolled. Then what is the probability of getting all? What is the probability of getting all of them getting all of them? What is the probability of getting all of them turning a number? Getting all of them turning a number greater than 4. Now this is a bachon ka khel. This is a bachon ka khel. Why? Because 3 dice are rolled and it's a compound random experiment. It's a compound Random experiment. So methodology 1 could be to count everything. Methodology 1 could be to count everything. Total possible outcomes will be 6 multiplied by 6 multiplied by 6, which is 216, which is 216. Favorable outcomes become favorable outcomes become 5 comma 5 comma 5 5 comma 5 comma 6, getting a number, all of them turning a number greater than 4 now, all of them turning a number greater than 4. So 5 comma 5 comma 5 5 comma 5 comma 6, and then 5 comma 6 comma 5, and then 5 comma 6 comma 6, and then with 5 all possibilities are covered. Now first place 6 5 comma 5, and then first one turns 6, second one 5, and third one 6. First one turns 6, second one 6, and third one 5, and first one 6, second one 6, third one also 6. Are we done? Are we done?
Yes, sir.
Yes. So total favorable outcomes are how many? Total favorable outcomes are, total number of favorable outcomes are 4 plus 4, 8. What will be the probability? Suppose you don't want to solve using multiplication law. Don't solve it using multiplication law, no problem. Don't solve it using multiplication law, no problem. Simply solve it using your single sample space. Because now you are pretending that I have a single sample space of 216 equally likely outcomes. Now you are pretending that I have a single resultant sample space of 216 equally likely outcomes. So you can still keep using your tariqas, your methods, your procedures that you used for single sample space. And you get 8 divided by 216 as the final answer. But this method can be very cumbersome if you get this method can be very cumbersome, very complicated it is going to become if you here you have to count only 8 things now. So you counted, no problem. But sometimes it's going to become so typical counting these many possibilities. The better thing is always to break that sample space into children's sample spaces. Break that sample space into children's sample spaces. So 1, 2, 3, 4, 5, 6, and I define an event getting a number greater than 4. And if I define an event getting a number greater than 4, what is the probability of that? Getting a number greater than 4 in a single throw of a dice. Getting a number greater than 4 in a single throw of a dice is simply 2 by 6. Once again, getting a number greater than 4 in a single throw of dice. Getting a number greater than 4 in a single throw of dice is once again 2 by 6. Getting a number greater than 4 in a single throw of dice is once again in a single throw of dice is once again getting a number greater than 4. Probability is simply going to be 2 upon 2 upon 6. Now I want probability of all of them greater than 4. All of them greater than 4. I want probability of all of them greater than 4. And if I want all of them greater than 4, I'm going to get simply, I use the multiplication law, and using the multiplication law, I again arrive at the same result. I again arrive at the same result. 2 by 6, 2 by 6 into 2 by 6, that becomes 8 upon 216. So multiplication law is such a beauty, no? Multiplication law is such a beauty. 2 upon 6, 2 upon 6, 2 upon 6. As a 12th problem, roll a die and draw a card. Roll a die and draw a card. You roll a die and you also draw a card. Okay. Now I want to get the probability of getting a number divisible by 6. Getting a number divisible by 6 and getting a number divisible by 6 and getting a numeric card of diamond and getting a numeric card of diamond divisible by 3. Actually, I'm so sorry, divisible by 3 and getting a numeric card of diamond. One tarika is you got to list all the possibilities on compound combined random experiment. On the compound combined random experiment, you got to list all the favorable possibilities. This method becomes impractical if S1, S2, S3, S4 become very large sample spaces. If S1, S2, S3, S4, S5 become very large sample spaces, the method 1 becomes a little impractical. So method 1 is simple, that you roll a die and you draw a card. So total number of possible outcomes will be how many? Total number of possible outcomes will be 312. Out of those 312 total outcomes, how many are favorable to you? You want to get a number divisible by 3 that satisfies by 3 itself, and then you want to get numeric card. Numeric card means 2, 3, 4, 5, 6, 7, 8, 9, 10. Jack is not a numeric card. Queen is not a numeric card. King is not a numeric card. Even ace doesn't count into numeric cards. So these are not numeric cards. Only 2 to 10 are numeric cards. Numeric cards are 2 to 10. Okay. Wait a moment. So I'm interested only in the numeric card of diamonds. Numeric card of diamonds. So how many are favorable to me? I get 3 on the dice and I get second of diamond. Then I get 3 on the dice and I get third card of diamonds. Then I get 3 on the dice, and I get fourth card on the diamond. Then I get 3 on the dice and fifth card on the diamond. 3 on the dice and 6 on diamond. 3 on the dice and 7 on diamond. 3 on the dice and 8 on diamond. 3 on the dice and 9 on diamond. 3 on the dice and 10 on diamond. Now, equal number of possibilities will come with 6 on the dice. So I can have 6 on the dice and 2 on diamond, 6 on the dice and 3 on diamond, 6 on the dice and 4 of diamonds, 6 on the dice and 5 of diamonds, 6 on the dice and 6 of diamonds, 6 on the dice and 7 of diamonds, 6 on the dice and 8 of diamonds, 6 on the dice and 9 of diamonds, 6 on the dice and 10 of diamonds. How many total favorable outcomes are there? This is, of course, a laborious, boring, cumbersome tariqa to do. Now that you have made a final rule, now that you have a final rule available, this is not a preferable tariqa to do. This is not a preferable way to do. This is not a preferable way to attack such problems. But it's still 1, 2, 3, 4, 5, 6, 7, 8, 9, and 9. Total number of favorable outcomes become 18. So you tell me what's going to be, the, are we using any multiplication law here? No. Are we using any addition law here? No. Are we using any Bayes theorem, blah, 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 blah? No. We are simply counting favorable outcomes and we are simply counting total outcomes. That's it. So this tariqa is relying on simply counting all possibilities. 18 favorable and 312 total. So in the event that I'm interested, it's going to have 18 upon 312. But the moment you identify it's a compound random experiment, it's always better to use multiplication law. The moment you identify it's a compound random experiment, it's always better to follow multiplication law of probabilities. Multiplication law of probabilities. So I'm going to have the second method, that my event gets satisfied by satisfying two events independently, getting a number divisible by 3 on dice, getting a number divisible by 3 on dice, and getting a numeric card of diamond, in drawing a card, getting a number divisible by 3 on 2 outcomes out of 6 possible outcomes, and getting a numeric card of diamond, diamond 2, diamond 3, diamond 4, diamond 2, diamond 3, diamond 4, diamond 5, diamond 6, diamond 10, divided by how many total possibilities are there in case of drawing a card? In case of drawing a card, total possibilities we have 52. So my dear friends, the first value becomes 2 upon 6, and the second value becomes 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 upon 52. You get exactly the same result. You get exactly the same result. I hope that now you have a very clear, crystal clear picture of how and when multiplication law can be used. I hope that now you have a very clear picture of how and when multiplication law can be used, when we can use multiplication law, and how we are going to use it. Perfect. Now we go ahead and try solving some problems on the combined application of addition law and multiplication law of probabilities. Let's go ahead and solve them. So we are at the topic probability 2.0, and in the probability 2.0, we understood multiplication law of probabilities, and now we go ahead and do some problems based on combined application of addition law of probability and multiplication law of probability. Addition law and multiplication law of probabilities. Tell me the score.
13, sir.
13, sir.
13. Okay. 13th problem, let's say Changu and Mangu are appearing for an exam. Changu and Mangu are appearing for an exam. An exam consists two papers. Exam consists two papers. Okay. Paper 1 and paper 2. Exam consists two papers, paper 1 and paper 2. Probability of Changu passing a paper from past record is 70%. Probability of Mangu passing a paper from past record is 80%. What is the probability of at least one of them at least one of them passing the exam. Changu and Mangu are appearing for an exam. And exam consists two papers, paper 1 and paper 2. From the past performance record, it is known that probability of Changu passing a paper is only passing any one paper is only 70%, and probability of Mangu passing any one paper is 80%. What is the probability that at least one of them is going to pass the exam? Write it once again, comprehend it once again, absorb the whole problem once again. Changu and Mangu are appearing for an exam. It consists two papers, paper 1 and paper 2. Changu passing any given paper, probability is 70%. Mangu passing any given paper, probability is 80%. What is the probability that at least one of them passes the exam? At least one of them. Passes the exam. That's why I said these are the problems based on combined application of addition law and multiplication law of probabilities. Combined application of addition law and multiplication law of probabilities. Just wait a moment. I need to create a little space. So Changu and Mangu are appearing for an exam. Consists of two papers, paper 1 and paper 2. Changu passing any given one paper, probability is 70%. Mangu passing any given one paper, probability is 80%. Probability of Changu passing any one given paper, probability is 70%. I actually like writing this thick, but this is the only problem with writing thick. Writing with this thick pen actually increases the speed, but this is the only problem, that it consumes a lot of space on the slide. So what is the probability of at least one of them passing the exam? Let's solve this. You need to learn to start breaking the problems into unions and intersections. At least one passing the exam gets satisfied either by Changu passing the exam and Mangu not passing the exam. Or there is one more way to satisfy your final requirement. Changu not passing the exam, but Mangu passing the exam. Or there is one more way of satisfying your final requirement, that Changu also passing the exam and Mangu also passing the exam. Changu passing the exam and Mangu not passing the exam, that is one way to satisfy the requirement that you have. At least one of them should pass. So at least one is passing. Changu is passing, Mangu is not passing. Then Changu doesn't pass the exam and Mangu passes the exam. And then Changu and Mangu both passes the exam. and notice how they are connected. You get satisfied even if this happens, or even if this happens, or even if this happens. You get satisfied when this happens, or this happens, or this happens. You need to learn. I told you in the beginning of this course that solving most of the probability problems will always be about breaking them into unions and intersections. So now you realize that you basically have to add 3 separate probabilities. You basically have to add 3 separate probabilities. So let's add 3 separate probabilities. Probability number 1 is Changu passing exam and Mangu not passing exam, plus probability of Changu not passing exam, Changu not passing exam and Mangu passing exam, or Changu passing exam and Mangu also passing exam. Let me remind you that R is replaced with the plus sign. Now, addition law has already been used. Addition law has already been used. Now I'm going to use the multiplication law because they are connected with 2 sample spaces. Observing Changu giving exam is 1 sample space, is 1 random experiment. Observing Mangu giving exam is another sample space, is another random experiment. And when I define a resulting random experiment of observing both Changu and Mangu, it becomes compound random experiments. Aha, probability, you beauty. It becomes compound random experiment observing Changu and Mangu, both of them together. Observing Changu alone, writing the exam is 1 random experiment. Observing Mangu alone, writing the exam is another random experiment. Observing both of them, writing the exam is a compound random experiment. Wherever your experiment has children random experiments, wherever your total experiment is broken into children random experiments, then you can use multiplication law of probability. Changu passing an exam and Mangu not passing the exam. Next one, Changu not passing the exam and Mangu passing the exam. Next one, Changu also passing the exam and Mangu also passing the exam. My dear friends, Changu passing the exam is 70% and Mangu not passing the exam is only 20%. Changu not passing the exam is 30%, but Mangu passing the exam is 80%. Changu also passing the exam is 70% and Mangu also passing the exam is 80%. Report the final answer. Report the final answer. 0.7 into 0.2 plus 0.3 into 0.8 plus 0.3 into 0.8 plus 0.7 into 0.8. 0.94 is the final answer. There are 94% chances that at least one of them will pass the exam. Can you now calculate that probability of at least one of them not passing the exam. Huh? You can calculate that. You can calculate that. Now, we solve another interesting problem based on combined application of addition law and multiplication law probabilities. Those who had patience in this journey so far, they are the real winners because my courses require exactly the same amount of patience that one should have while watching first few episodes of Breaking Bad. Every course of mine is as boring in the beginning as watching first few episodes of Breaking Bad. But once you can survive 3, 4 episodes, then you know that you're not going to stop. Then you know that you get addicted. चखना मत, आदत बिगड़ जाएगी. My dear friends, we go ahead and solve another interesting problem based on combined application of addition law and multiplication law. This is going to be the 14th problem of the chapter. There is a bad news, guys. There is a bad news. Changu got arrested. Changu got arrested today. Changu has got arrested today against the charges of stealing cash. Changu got arrested. Probability of Changu lying probability of Changu lying is 60%. And probability of a correct report given by lie detector. Probability of a correct report given by lie detector is 87%. What is the probability of Changu getting a clean chit from court? What is the probability of Changu getting a clean chit by the court? What is the probability that Changu will get freed by the court? Changu has got arrested and the charges are that Changu stole some cash. Probability of Changu lying is 0.6 and probability of a correct report given by lie detector is 0.87. What is the probability that Changu will not be convicted? What is the probability that Changu will not be convicted? No conviction will happen. No conviction will happen. What is the probability that no conviction will happen? Conviction नहीं होगा, आरोप तय नहीं हो पाएंगे, आरोप सिद्ध नहीं हो पाएंगे, इस बात की क्या प्रोबेबिलिटी है? How Changu can be saved? Let's save Changu. So Changu can be saved that there is no conviction. He is not convicted by court. That's possible. That's possible in That's possible in two manners. One, Changu speaks the truth. He's naturally saying that I did not steal. I did not steal the cash. So let's say he is speaking the truth, but his truth must be verified by the lie detector. So his truth must be, let's say he speaks the truth, and the lie detector says that yes, he is speaking the truth, and the lie detector validates it. Let's say he says, I did not steal the cash, and let's say he actually did not steal the cash. He says that no, my lord, I was not even present there. I went to the satsang of Swami Chinmayanand with family. So I was not present. Let's say he is speaking the truth. Let's say he is indeed speaking the truth. And the lie detector validates it. Yes, this man is speaking the truth. He was not present when the robbery was done, when the stealing was done. But notice that there is one more way. Notice that there is one more way of Changu getting freed. And that one more way is, this is one entire way. He says truth and lie detector validates it. There is another way that he has actually stolen the cash, but he says, no, I did not steal the cash. So he is lying. Another possibility could be there that he actually stole. He actually is a thief. Changu chor hai, Changu chor hai, Changu chor hai. Changu is a chor. He is lying. He says that I did not steal the cash, but he's actually lying. He is the thief. But Changu is lying, and lie detector is unable to catch that lie. He's again saved. Changu is lying that I did not steal the cash. Actually, he stole the cash. He is only lying. Okay? He did not steal the cash, and he says, I did not steal the cash. That becomes the truth. And the lie detector machine validates it, that this guy is saying the truth. But another possibility in which he can be saved, that suppose he actually stole the cash, but in the court he says that no, I did not steal the cash. And lie detector is unable to catch his lie. And the lie detector is unable to catch the lie. So, my dear friends, he speaks the truth and lie detector validates it. That is one way he can be saved, that he is actually innocent and lie detector helps him. Another way he can be saved, that he is not innocent. He committed the crime but lie detector is unable to catch him. One way is he's actually innocent and lie detector supports him. Another way is that this guy is not innocent. He committed the crime. He committed the crime. He's obviously going to say, I did not steal the cash. Which thief is ever going to say that I did it? Huh? Rare scenario. So he's lying, and unfortunately, lie detector supports him again. Lie detector unable to catch the lie. This is one more way. These two possibilities are obviously mutually exclusive. Either first one is possible or second one is possible. Either he's innocent or he's actually guilty. Either he's innocent or he's actually guilty. He speaks the truth. So, because these two possibilities are connected with, or because these two possibilities are connected with, or I'm going to I'm going to break these two possibilities with a plus, speaks truth, speaks truth, and lie detector validates plus he's lying and lie detector unable to catch. He's lying actually, but lie detector is unable to catch. Bechara Changu. Poor helpless Changu. Just now he was writing exam with Mangu, and all of a sudden police came. He speaks truth, and lie detector validates it. Or he is not speaking the truth, and lie detector fails. His chances of stealing the cash are 60%. Drishyam 3.0, exactly. 0.87 plus 0.6 into 0.13. His chances of committing the crime are 60%, and not committing the crime are 40%. But his chances of not getting convicted are a little higher than his chances of not committing a crime, and that's 42.6%. Thanks to thanks to the inefficiency of lie detector machine. But unfortunately, there is also a chance of him not committing the crime, and yet lie detector says that he committed the crime. So can you calculate the probability of Changu getting convicted? That's on you. Next class, we will start at 2:30 and probability will continue. Next class, we are going to start at 2:30 and probability will continue. Thank you so very much, people.
Okay, sir. Thank you.
We'll do some more problems based on application of addition law and multiplication law, combined application of addition law and multiplication law. And next class is going to introduce the last leg and one of the most beautiful legs of probability, that is conditional probability. See you guys at 2:30. Bye-bye.
Sir,
Yes.
sir, I have one doubt on engineering mechanics, sir.
One doubt on engineering mechanics. Okay. What's your doubt?
Sir, that BEQ question, sir, which belt friction. One
Sorry?
side there was 200. Sir, last BEQ question, sir, for belt friction.
Okay, answer is not matching.
Yes, sir, I am getting about angle of 29 point
You are
something.
talking about this question, na?
Yes, sir, one side there was 200
You're
kg
talking
weight.
about this question, na? This question.
Yes, sir.
This answer is probably provided answer is wrong. I will update it.
Okay, sir. Thank you, sir.
Okay.